Runway is blocked. Go around.
Go around.
Engine fire stopped.
Continue.
Flaps, silence the bell.
We have fire.
Identify.
You have fire.
Engine failure number 2.
Flying is much safer than you might think. Today, flying has undoubtedly become one of the safest means of transportation. Traveling on an airliner is more than 2,000 times safer than driving your car to the airport. This extraordinary safety comes from the technical development of airplanes, the strict specifications, and, last but not least, thorough pilot training. You might think that the profession of pilots and flight attendants is what you can see on each flight or in some movies. This, however, is just the tip of the iceberg. Few of us know that the smiling flight attendants serving us drinks are not there primarily to look after our comfort, but rather to ensure our safety. And behind the scenes, they regularly practice how to handle emergencies. The same is true of airliner pilots. When you watch them in the cockpit, you can only see the surface. Their real skills and roles start with challenging situations and emergencies. This film is about how pilots can handle situations which are more or less special. We'll also understand that besides modern technology, pilot training also plays an important role in the safety of aviation, even in emergencies. Flying is much safer than you might think. One of the highlights of the House of Future exhibition at Millenarisch Park in Budapest is a flight simulator that is an exact replica of the cockpit of a Boeing 737 NG aircraft. The displays and over 100 switches of the cockpit work exactly the same way as in the real thing. The heart of this simulator is Microsoft's very popular software Flight Simulator, which you can install even on your home computer. With over 20,000 airports in the simulator software, you can fly anywhere in the world, explore places you've never seen before, fly all kinds of aircraft, from the biggest ones to the smallest, test your skills in different weather conditions, and meanwhile, learn the ins and outs of navigation and piloting. The flight simulator at the House of Future Center was designed and built by András Kozma.
A szimulátor összesen 5 darab PC vezérletével működik. Az 5 PC közül egy az, ami magát a tájat, tehát a flight szimulátort dirigálja, és az összes többi a cockpit különböző funkcióit, a repülőgép szerkezeti dolgait rakja össze egy kerek egészé. 3 projektor az, ami körbevetíti a képet, amit látunk. Mint szimulátorról tulajdonképpen azt mondhatjuk el, hát mindenekelőtt azt, hogy nem mozog, tehát nincsenek hidraulikus elemei, viszont az eredeti repülőnek 90-95%-a az, amit gond nélkül szimulálni tud, amiben beletartoznak természetesen a különböző rendszerek egymásra való hatásai is. Azaz, hogyha valaki egy ilyen szimulátoron akarja az eredeti gép repülését megtanulni, én azt hiszem, hogy viszonylag elég könnyű dolga van.
In the past, the flight crew working in the cockpit of an airliner often consisted of 4 or even 5 people, because apart from the 2 pilots, there was also a radio operator, a navigator, and a flight engineer. So almost every set of instruments required an additional crew member on these aircraft.
So papers on board before start procedure, please.
Thanks to modern technology, today's airliners are flown by only 2 pilots, who can handle every task required to operate the aircraft safely.
And the checklist.
The captain sits on the left. He always has the final word during emergencies and is responsible for everyone's safety on board. The captain can take control of the aircraft at any time and has the right to change the flight route if necessary. Flight attendants must also report to the captain and follow his orders.
126, rotate 129.
Sitting on the right, next to the captain, is the first officer. Although he's below the captain in rank, he is also fully trained to fly the aircraft by himself.
Takeoff briefing. It's completed. Anti-collision light on, flight deck door is closed before start. Checklist completed.
Okay, we are clear for start. Starting sequence number 2 and 1.
Okay. And commencing.
Despite the uniforms, the epaulets, and the rank system, pilots' cooperation is not based on hierarchy, but rather on working together as a team and sharing the tasks in a logical and safe way. The 2 pilots work together. In addition to sharing the tasks according to precisely laid out procedures, the pilots always check each other to eliminate any mistakes. Another reason why we can find 2 pilots on each airliner is because should one of the pilots become incapacitated, the other crew member can take the controls and land the plane. The procedures and tasks to be carried out by each pilot are precisely described in what is called multi-crew cooperation, or MCC for short. The details of these procedures vary from airline to airline, but the basic safety principles remain the same. One of these basic rules is that only one of the pilots can fly the aircraft at any given time. Imagine what it would lead to if cars had 2 steering wheels and the 2 people in the front seats had no idea which one of them was actually driving. This should never happen in the air, so only one pilot flies the plane, the other only helps out by following instructions, handling radio communication with air traffic control, setting navigation frequencies, and checking instruments and switches so that his colleague can really concentrate on flying the aircraft. The pilot who is flying the aircraft is called pilot flying, or PF, while the other crew member is referred to as the pilot monitoring, or PM. These roles are usually swapped after each landing. If, for example, on an outbound flight the captain is the pilot flying, and the first officer takes the role of the PM, the assisting pilot, then on the return flight the first officer flies the plane from the right seat with the captain assisting.
Line up.
Line up.
Left side clear.
Right side clear.
And take off.
Use take-off pressure. Taking.
Let's check.
P1 and rotate. Positive rate.
Yeah.
Thousand.
And 1, speed 210. Descent checklist, please.
Descent checklist. Recall. Cross check.
Checked.
There is a simple,
Checked. Auto
yet
brake.
very efficient tool that enhances safety to a very high degree. Checklists.
Okay.
Checklists, which are compulsory, help pilots check the correct positions of important switches, set up various instruments, and perform certain tasks in each phase of flight, and on every flight. Checklists are always read out by the assisting pilot.
And the landing checklist.
Landing checklist. Engine start switches. Continuous. Speed brake. Arms. Landing gear down. Flaps. 30. Green light. Landing checklist completed.
Checklists must be used before starting the engines, after engine start, before takeoff, after takeoff, when approaching the airport, before landing, and after shutting down the engines. Checklists play a very important role. Repeated tasks are carried out routinely in the cockpit day after day, so checklists help maintain pilots' attention and alertness.
Minimum contact landing.
Speed brakes up.
Så långt.
Shut down. Shutdown checklist.
Checklist, please.
Fuel pumps off except one for APU. Pitot heat off. Hydraulic panels set. Flaps are up. Parking brake.
Set.
Engine start levers.
Cut off.
Shutdown checklist complete.
The question of why airplanes can fly is answered by the complex equations of aerodynamics. But as a simplified summary, we can say it's the wings, more precisely, the air moving around the wings and not the engines, that keep an airplane airborne. So the secret is the shape of the wing, or rather the fact that air travels a shorter distance below the wing than past its upper surface. Air that moves faster is more tenuous, therefore its pressure is lower. As a result, an upward force called lift is generated on the upper surface of the wings. This force moves the wings and whatever is attached to it upwards, and thus the aircraft can stay in air. All you need for this to work is speed or moving air. Since lift also depends on the speed of moving air, when it comes to landing, one of the decisive factors is wind direction and strength. Odd as it may sound, the most favorable condition is a headwind, as it increases the rush of air past the wings. Because some of this moving air is generated by the headwind, the airplane can fly at a lower ground speed, and lower speed at touchdown also means a shorter brake distance, reducing the risk of rolling off the runway.
+5.
This is why backwind, called tailwind, should be avoided, as its effect would be just the opposite. To maintain the required rush of air around its wings, and thus generate enough lift, the plane would have to fly faster. This would increase the touchdown speed, making it harder to stop. However, things are not always this simple. A runway has only two directions, and the wind may blow at an angle to the runway direction, or even perpendicular to it. This is called a crosswind. Under such conditions, the airplane can't approach the airport in the usual way, which means crossing the extended runway center line and then turning towards the runway. This technique wouldn't work in a crosswind, because the aircraft would constantly get blown off the runway center line, and the pilot would have to keep correcting the heading. To stay on the required straight course during a crosswind landing, pilots use a special technique called crab landing. The basic idea of the crab landing technique is to turn the nose of the airplane into the wind to compensate for the drift caused by the crosswind and to stay on the extended center line of the runway. A bit of mathematics. If the landing course is 360 degrees, that is exactly north, the speed of the aircraft during the approach is 140 knots, and the wind is blowing from the west at 30 knots, then correcting the vectors gives us the required heading adjustment, the alpha angle. Here's the equation for calculating the required heading correction. Beta is the angle between the designated course, called the runway heading, which is north, and the wind direction, west. W stands for wind speed, and TAS means the speed of the airplane. The equation yields the heading correction, the alpha angle, which is about 12 degrees. So the pilot must point the nose of the airplane 12 degrees left of the final course to stay on the required track to the runway. But pilots don't have to be math geniuses. They can use their instruments to check the drift, or, in good visibility, they can compensate for crosswind visually, simply by looking out of the cockpit window. It just takes some practice.
Gear down.
Gear down.
Flaps 15.
Flaps 15.
Crab landing is a tricky technique, because you have to keep the aircraft on the extended runway center line, while the nose of the airplane is pointed off-center. Let's see a crosswind landing in the simulator. For the demonstration, we have set a very strong crosswind of 40 knots at the airport in Stuttgart, Germany. The airport has only one runway, so in reality, and in such extreme wind conditions, safety would come first, and approaching planes would either wait or divert to another airport. But in the simulator, we can just go ahead and try to land. Now, the first officer is the pilot flying, while the captain on the left is helping out.
Set VRF plus additive. Check.
plus dämsat.
VREF is the minimum safe speed at which an airplane can stay airborne during landing. To be on the safe side, pilots always choose a slightly higher speed to prepare for any unexpected gust of tailwind.
Landing checklist starts, which is continuous speed brake, armed, landing gear, down 3 green, flaps, 30-30, green lights.
The primary flight display, or PFD, in front of each pilot shows all the important flight data. The artificial horizon in the middle indicates the angle of the airplane relative to the horizon. On the left, you can see speed in knots. Your altitude is on the right side, with the little needle showing your current rate of climb or descent.
Wind check.
030 degrees, 40 knots.
Things get quite tricky on touchdown. While airborne, the nose of the airplane doesn't have to point in the actual direction of movement. But for touchdown, care must be taken as the landing gear, particularly the nose wheel, might not be able to absorb the side forces. When the nose wheel touches the runway, the nose of the plane must match the direction of travel, which is the actual ground course. The ailerons, the control surfaces on the wing, can't be used for this heading correction, as banking the plane left or right very close to the ground would be dangerous, and the wings should be kept level during touchdown. So pilots use their rudder pedals instead. Moving the pedals deflects the rudder, the huge vertical control surface in the tail, causing the nose of the airplane to move left or right. On touchdown, pilots use the rudder pedals to realign the airplane with the direction of travel.
400.
Visual.
300. 200. Approaching minimums. 100. Minimums. 40. 30. 30. 20. 10.
Although performed routinely, landing in reduced visibility due to fog, haze, or precipitation is very exciting. Today's modern airliners can land safely even in such weather conditions, but the procedure demands more attention than approaches flown visually in good weather.
Cleared for approach.
In the simulator, our pilots are now approaching Ferihegy Airport in Budapest, where we have set ground fog and visibility of about 200 meters. ferry hedge, just like at any other airport with the necessary equipment, a Boeing 737NG can land safely, even in very low visibility. But this requires the use of the aircraft's automatic systems, the autopilots, while the crew has to follow a so-called precision approach procedure. For precision approaches, there's a system called Instrument Landing System, or ILS. At airports equipped with ILS, special radio signals provide an invisible tunnel that can precisely guide an airplane down to the runway. The ILS consists of several devices, one of which is a UHF radio transmitting a radio beam from the other end of the runway. The radio beam is called localizer and abbreviated as LOC. The instruments on an aircraft detect and interpret the signals and display the deviation from the ideal course. The autopilot can follow the radio beam automatically and fly a precision approach to the airport, even in very poor visibility. In the cockpit, at the bottom of the primary flight display, a magenta diamond moving on a horizontal scale shows the deviation from the localizer. When the diamond is at the middle, the aircraft is right on the final course. If the diamond moves to the left, the designated path is also to the left, so the aircraft should alter its heading to the left until the diamond is centered. Another part of the instrument landing system is a transmitter placed next to the runway threshold and transmitting on a separate frequency. This radio beam designates a vertical path that a descending aircraft has to follow in order to touch down at the beginning of the runway. This radio signal, helping descent, is called glide slope and abbreviated as GS. Deviation from the glide slope is shown by the magenta diamond moving up and down along the right side of the primary flight display. While the aircraft is below the descent path, the diamond stays at the top of the scale, indicating that the glide slope is above. Normally, an aircraft should capture the glide slope from below and then follow it with a continuous descent. If the diamond moves downwards from the center of the scale, the aircraft is above the glide slope, so a faster descent is necessary.
Localizer capture.
Checked.
To sum up, the ILS is a navigation system that makes it possible to carry out a precision approach and a safe landing even in extremely poor visibility. Both approach and the landing can be carried out automatically. ILS approaches have different categories. A Category 1 approach, or Cat 1, requires a minimum decision height of 200 feet, shown as DH in the table. This means that an aircraft flying a Cat 1 approach may descend to 200 feet. If at this altitude the runway is still not visible, pilots have to abort the approach and go around. RVR stands for Runway Visual Range, and it's used to describe the horizontal visibility along the runway. The minimum visibility for Category 1 is 550 meters. The rest of the approach categories have gradually decreasing decision heights and visibility minima. For example, the decision height for Cat 2 is 100 feet with a minimum visibility of 300 meters. Cat 3A approaches may be flown with a decision height of less than 100 feet and in less than 300 meters of horizontal visibility, whereas the decision height for a Cat 3B approach is only less than 15 feet or 15 meters. Cat 3C does not even have any minima and allows landings even in zero visibility. Our pilots are now flying a Cat 3B approach to runway 13 left at Ferihegy Airport, Budapest, Hungary.
Flaps 5.
Performing a Cat 3 approach requires a lot of training. The captain and the first officer have to work together. There is a higher level of alertness in the cockpit when pilots have to rely solely on their instruments. In very low visibility, should any problem arise, timely and accurate pilot intervention is crucial. During a Cat 3 procedure, the aircraft flies automatically, with both the controls and engine thrust operated by automatic systems. The crew set the required flight modes and keep a sharp eye on the autopilot. Approaching the localizer radio beam, the autopilot turns towards the final course and then keeps the airplane on the radio beam. For safety reasons, a full automatic Cat 3B landing requires the simultaneous use of at least 2 autopilot computers, which constantly monitor each other's operation.
Engage command B. Gear down, flaps 15.
The word flaps refers to the mechanical parts that change the shape, or in more technical terms, the profile of the wings. When pilots move the flaps lever on the thrust quadrant, wing surfaces, called slats and flaps, extend from the leading and trailing edges of the wings. Flaps and slats increase the surface area of the wing and also its curvature. This increases lift, so the aircraft can remain airborne at a lower speed. But increased curvature also means higher drag, which is the price to pay for the added lift. Usually, 30 degrees of flaps is used for a normal landing, and 40 degrees for a fully automatic procedure. For takeoff, flaps are set at their 5 or 15 degree position. When the autopilot detects that the aircraft has crossed the glide slope radio beam, the white GS sign, indicating the pre-selected automatic glide slope capture mode, activates and changes to green.
Checked. Glide slope capture.
Checked.
Flap 15, green light.
Flaps 30. Flaps 40.
Flaps 40.
Landing checklist, please.
Landing checklist. Engine start switches. Continuous. Speed brake. Armed. Landing gear down. Flaps. Stand by for flaps. Now 40. Flaps 40, green light. Landing checklist is complete. Flare armed.
Checked.
During a fully automatic landing, flare and rollout appear at the top of the primary flight display.
1,000.
This is how the computer tells the pilots that it is ready to carry out the landing and touchdown fully automatically.
$500.
500.
Checked.
Close to the ground, pilots are helped by an instrument called the radio altimeter, or RA. This instrument emits radio signals downwards and calculates the exact altitude based on the reflected signals. The system also gives automatic altitude callouts to the pilots, which is the odd machine voice counting backwards in the cockpit.
400.
At 150 feet from the ground, 100 feet from the decision height, both the first officer and the automatic systems warn the captain that a decision to land is imminent. The call-out is approaching minimums.
200.
Approaching minimums.
Approaching minimums. 100.
At this point, the captain should look out of the window. If he can see the runway, he should announce landing and land the airplane manually, or simply let the autopilot finish the job.
60. Minimums.
Minimums. 40.
And you contact
30.
landing.
20. 10. 10.
Speed brakes up.
Reverse around